Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of this week. In the previous lecture, we started discussion on Gaussian Quadrature, which is a numerical technique for integrating any function. Now, what we do in Gaussian Quadrature technique, we had seen that the idea is over the domain, take some integration points and evaluate the function on those integration points, and then weighted sum of those function values at the integration points will give you the integration. Now, the concept wise, it is not very different than the other integration, other quadrature rule available, but salient feature of the method is those integration points are optimum, and with a minimum number of points we can integrate any polynomial exactly, provided the rules of integration is chosen properly. By rules, I mean whether it is 2-point integration, 3-point integration, and so on. How many Gauss points to be taken? If that is chosen properly, we can show that polynomial can be integrated through this method in an exact sense. Now, we have seen how to determine these integration points, and we have also seen how to find out the weight associated with the integration points. Now, today what we will do is, today we will extend the concept to higher dimension, to two-dimensional problem. But today's lecture will not involve any detailed derivation. We had already derived the formulation to understand the method. Today we will just extend it to different domain in two-dimensional problem and then demonstrate it through one example. Okay. So, this is the problem now we have. We need to integrate any function f, which is a function of x and y, over an element, or say forget about element for the timing, over a two-dimensional domain. We need to find out the, we need to see how it is to be done. Now, let's first do it for a quadrilateral element. Now, we'll follow the same approach. It is a physical domain, any x in xy coordinate. Suppose a function is defined on this domain. Now, this is called physical domain. I and j are the unit vectors along x and y. We will use them shortly. Now, we define another domain which is called the parametric domain, and the coordinates in parametric domain is called natural coordinate. So, very similar to one dimension case. In one dimension it was -1 to 1. In this case it is x direction, z direction in -1 to 1 and eta direction -1 to 1. So, this is the parametric domain. Now, we need to define a map between these two domains, and then take a small element in the parametric domain. Suppose this corresponding image in the physical domain. Suppose this. Now, this can be this can be obtained. This image can be obtained through this map. Now, this map we have already seen the shape functions. Through that shape function, this map can be constituted. Now, so what we have to do now is, suppose this is the area, is a small infinitesimal area, that is d xi d eta, and the area of this domain is say d omega. Okay. Now, so we know the area of this, that is d xi multiplied by d eta, but we need to find out what is the corresponding area when this area is mapped to the physical domain. What is the area in that of that image? That we need to find out. Now, take two vectors, say vector A and vector B. Now, we know that these two vector A can be written in terms of can be written as this, where dx del x del xi we will not write explicit expression for del x del xi. It all depends on how all depends on the map, this map, right? How you write the map. Now, but if we see, suppose it is straight sided, we have a square domain and it is a straight sided quadrilateral, like 4 noded quadrilateral. We have this map is a linear map, right? Now, but then we can have a different quadrilateral also, but for that particular domain this map needs to be written. So x as a function of xi we already know through that safe function. Now, so similarly b can be written like this. Now, once we know the vector a and b, their cross product will give me the area of this d omega. So d omega can be taken as the scalar triple product, which is this a and b are the vector and k is the unit vector normal to the area. I and j are the unit vector along x and y direction. So these can be written as in a matrix form as this. Okay. Now this is, if we evaluate, this will give you this determinant of this matrix. Okay. Now this is essentially the Jacobi. Now, so then the small d omega can be written as like this. Now in the integration, what we will do now? We will in the integration, this d omega will be replaced by this, and the function is written in terms of variable x and y, that now needs to be written in terms of xi and eta. Okay, so this function now can be written as this. So this was, now our parametric domain is between -1, xi is -1 to 1, eta is -1 to 1, and then integration will be this. F xi and eta is f x y, but written in terms of xi and eta coordinate system integration. So this is I. Now we apply the quadrature rule, Gaussian quadrature rule. Idea is we take few points on the domain and calculate the function values at those points, multiply by their weight and sum them. Now this is the rule. So if it is an n point rule, now this is very important. In one dimension case, we had only one summation, right? So along that xi axis we have to take, if it is an n point integration rule, we have n points along the axis, and at every n point we have to determine the function values. But now it is a 2-dimensional case, so the summation is over zeta coordinate and over eta coordinate. Okay, and okay, so and wi and wj, wi is this wi is associated with this coordinate zeta coordinate, and dj is associated with eta j coordinate. Now if we will do one example, and through that example probably this will be more clear. Now this is the integration. Now quadrature points and the weight, integration points and the weights for quadrilateral domain, we can directly take the integration points we already have derived or obtained for one-dimensional case. The same points we can take, but now suppose these are the integration points, the positions of the integration points, representative positions of integration points for different quadrature rule shown. Now for n point quadrature rule, we have just one integration point, and then that integration point is at 0, 0, and the weight is 2. Now for 2 integration point, we have, for 2-point rule, n is equal to 2, we have 4 points. 4 points because along zeta direction you have 2 points. Rule is 2, so along zeta xi direction we have 2, and along eta direction we have 2. So in this direction we have 2 points, and in this direction also we have 2 points. Now what are the coordinates of those 2 points? Now when we move in this coordinate, in xi coordinate, xi direction, our positions of the integration points will be -1 by root 3 and +1 by root 3. Means for this point xi will be, this is 1, this point xi will be -1 by root 3, and for this point xi will be 1 by root 3. Similarly, if we take this, for this point xi will be -1 by root 3, and for this point xi will be 1 by root 3. Okay, so in xi direction we have only 2 points. Now if we move in eta direction we have this layer is in eta direction. First integration points on this line and the second integration points are on this line. So at this line, at this point, eta will be minus 1 by root 3 and at this point eta will be 1 by root 3. Similarly, at this point eta will be minus 1 by root 3 and at this point eta will be 1 by root 3. This is how, but the same thing we can do for other integration rule as well. Now before we move on and then see how the integration to be performed for other domains, a triangular domain, let us take one example for a better comprehension of the method. Okay, so let's take a function fxy. Fxy is defined as, say, x square then plus xy square plus y cube, and suppose this function is defined over this domain, a rectangular domain, and this is minus 1, the coordinates are minus 1 1 and then this coordinate is 3 1 and this is 3 5 and then minus 1 and 5. Now I want to integrate this function over this domain, so that integration will be I will be integration x is equal to minus 1 to 3 and then y is equal to 1 to 5 and fx is x square plus xy square plus y cube dx and then dy. Okay, now we can have this integration in closed form, and if we do that then E exact is equal to 826.6667. So this is my E exact. Now we will compute the integration using Gaussian quadrature and then compare our result, numerically obtained integration, with this. Okay. Now first we need to, this is a polynomial, so this quadrature rule, through this quadrature rule we can integrate polynomial exactly, provided integration rule is chosen properly. And integration rule, how to choose integration rule, we know that for an n point rule can integrate a polynomial up to 2n minus 1 order. So any order of polynomial less than 2n minus 1 can be integrated exactly with a rule, with n point rule. Okay. Now let's see what rule we required for this polynomial. Here our polynomial is cubic. So if we take n is equal to 1, so 2n minus 1 means 1. So we can, with 1 point rule, we can integrate only linear polynomial. If we take n is equal to 2, so 2 into 2 minus 1 means 3. So we will use 2-point quadrature rule, through which we can integrate a polynomial, a cubic polynomial exactly, and our polynomial is cubic. So let us take a 2-point quadrature rule. Okay. So first thing we have to do, if we recall the Jacobian, we have to find out a map. Our parameter, this is a physical domain, right? This is physical domain. And our parametric domain is, if you recall, and parametric domain, our coordinate is natural coordinate. This is plus 1, minus 1, minus 1, and this is 1 1, and this one is minus 1 and 1. Okay. So first we need to find out a map between this domain and this domain. So x needs to be written in terms of xi and eta, y needs to be written in terms of xi and eta. Let us do that. So x is equal to, from this we can write x is equal to 1 plus 2 xi. You can verify this, and y is equal to 3 plus 2 xi. So xi is equal to minus 1, we will get x is equal to minus 1, xi is equal to plus 1, x is equal to 3. Eta is equal, this will be y is equal to 3 plus 2 eta. So eta is equal to minus 1, y is equal to 1, eta is equal to 1, y is equal to 5. So this is the map. So Jacobian, we can write Jacobian. Jacobian is equal to, we know, del x, del xi, and then del y, del xi, del x, del eta, then del y, del eta. So if we substitute this will give me del x del xi is 2, this is 0, this will also be 0, and this is 2, okay. So for Jacobian, determinant of Jacobian is, determinant of Jacobian is equal to 4. In this case Jacobian is constant. So since Jacobian is constant, we can take the Jacobian out of the integration. Okay, so now what we will do now is we will take different points for 2-point Gauss quadrature rule. So our integration points will be, our one point will be here, another point is here, another point is here, and another point is here. Okay, now suppose this point is, for this point it is xi1 and eta 1, okay, and this is xi2 and eta 1. Similarly, this is xi1 eta 2, and this is xi2 and eta 2. And xi1, xi2, coordinate of xi1 and xi2 are what? Coordinate of xi1 is minus 1 by root 3, xi2 is plus 1 by root 3, eta 1 is minus 1 by root 3, and eta 2 is plus 1 by root 3. Now, so next we take the table, we write the table. So first is Gauss points. We have, first point is 1, 1. First point is means xi1 and eta 1. Second point is xi2 and eta 1. Third point is xi1 eta 2, and fourth point is say xi2 and eta 2. There are 4 points. So what is xi? This is xi and eta. The first point is xi will be minus 1 by root 3 and eta will be minus 1 by root 3. Xi will be 1 by root 3, xi2 will be, eta will be minus 1 by root 3. Xi will be minus 1 by root 3 and eta will be 1 by root 3. And finally, this will be 1 by root 3 and this is also 1 by root 3. Okay. Now we have to evaluate the function value. Now function value is function of xi and eta. We have in this expression, the function in this expression, it is written in terms of x and y. We already know x, relation between x and xi, and y and eta. So this function now needs to be written in terms of xi and eta. So let us write here this function f of xi and eta will be 1 plus, this is x square means 1 plus 2 xi, 1 plus 2 xi whole square, plus we have x into y square means 1 plus 2 xi into y is 3 plus 2 xi. Let's take y is equal to 3 plus 2 xi, 3 plus 2 eta whole square, and then finally y cube, y is 3 plus 2 eta plus 3 plus 2 eta whole cube. So this is f xi, right? So we have to evaluate f xi. And then weights. Now if we look at the weights for this 2-point quadrature rule, is all are 1. So weight is 1 here, weight is 1, here also weight is 1, here also weight is 1. Let us evaluate for xi eta this, and I'll just write the expression here. It will be 5.7806, and then this will be 18.2633, and is 69.0701, and finally this is 113.5527. Okay. Now integration is what? Integration is, so what we have done is we have to integration will be summation of I is equal to 1 to 2 summation of j, which is equal to again 1 to 2, and then Jacobian for us it is constant, so let us write it here, wi and wj, then function of xi I and eta I. Okay, so this is all these 4 terms. Or this 4th term multiplied, wi will be 1 1 1 1, finally Jacobian is equal to 4 we have seen. So this will be Jacobian is equal to 4 multiplied by 206.6667. 206.6667 means this summation of all this plus this plus this, okay, and this give us 826.6668, and I exact was 826.6667. Okay, so this is how we can apply this Gauss quadrature rule for quadrilateral element as well. Now, as I said, in this case our map is very straightforward. By looking at it we can develop the map, but you can have a system like this. We can have a physical domain like this, and then parametric domain is this, and this map needs to be defined, and through this map Jacobian needs to be calculated, and once this Jacobian calculated, then the same straightforward this rule, through this rule we can calculate the integration. So this is how it can be done for higher dimension. Now let's go back. Next, quickly see if I have to do the integration in other element, other domain, say triangular domain, how it is to be done. So for triangular domain it is for triangular domain this integration is like this, where xi1 and xi2 are the natural coordinates. Now this is the integration wi. Now here the rule is n is equal to, for here n is equal to how many Gauss points you have within this element. If you have 3 Gauss points, then it is 3, n is equal to 3. If you have say 7 Gauss points, then n is equal to 7. So it all depends on how many Gauss points you have within this element. Okay, now we will show the for different rule what are the coordinates of the Gauss points, what are the coordinates of these integration points, and what are the weights. Okay, but the essence of the method remains same. Calculate the value at these Gauss points, and then function values multiplied by Jacobian, sum it, get the integration. Okay, now this is the Jacobian, same, we know the map. If we have we have a triangle in physical domain. That physical domain needs to be mapped with the parametric domain, and then through this map we can get this Jacobian. Now for a straight sided 3-node triangle, we can show that for something like this 3-node triangle, and then this Jacobian can be explicitly written like this. We can verify this. So for that we don't have to write it through shape functions and differentiate it with to get the Jacobian. We can directly get Jacobian like this. Now, so these are the integration points. For 3-point rule, we have these are the 3 points, and the coordinates of 3 points are given, and the corresponding weights are given. Xi1 I, Xi2 I means this is at this point. This point coordinate is this and this. In Xi1 direction this, Xi2 direction this. Similarly, at this point coordinate is Xi1 direction this and Xi2 direction this, and at this point Xi1 direction this and Xi2 direction this. So this is 3-point quadrature rule. Similarly, we can have 7-point quadrature rule like this. The numbers are shown here. So first point is coordinates are these, Xi1 and Xi2 direction. This is the first point. Similarly, second point's coordinates are this. This is the second point. Similarly, these are third points, coordinates are this, and fourth point, fifth point, sixth point, and seventh point. It is very important you see the order of the points, and then corresponding weight we have to take. These are the corresponding weights. Okay. Now the rest is simple. We need to calculate these values, function values. Any function we need to integrate at these integration points, multiply by their weight. Jacobian we know, the transformation between the physical domain and the natural and the parametric domain, get the integration. Okay. Now this is how this numerical integration technique, Gaussian numerical integration technique, can be applied, and this is very useful in our course, because you will see that whenever we apply, most of the time whenever we apply finite element method, we need to integrate the weak form over the element. We will use this technique because most of the time our shape functions are polynomial. Okay, just before we close today, this is particularly for a triangular domain and the straight-sided triangular domain. Straight-sided triangular domain like this or like this, then any monomial can be integrated exactly like this. Is the formula for integration when A is the area of the triangle, when Xi and Xi1, Xi2, Xi3 are the natural coordinates, also called triangular coordinates. Okay, so in that case, if we have to integrate a monomial like this over a triangular domain, and our domain is straight-sided, then we don't have to do integration numerically. Straight away applying this formula, we can get the integration. Okay. Now, so this is the integration technique. So this week, this week our objective has been to set up the tools required to apply finite element method in 2-dimensional problem. Next week what we will do is we take a specific problem and write the weak formulation of that problem, and then we'll apply finite element method to get the solution of those boundary value problem. With this, let us conclude this week. See you in the next week. Thank you.